You have seen photographs of every planet in the solar system, scrolled past them in textbooks, on phone screens, in documentaries you half-watched on a Tuesday night. If someone asked you to picture Uranus, you would imagine a pale blue ball with nothing on it. That image was wrong. In December 2023, the James Webb Space Telescope captured Uranus in infrared and revealed a planet covered in storms, wrapped in glowing rings, surrounded by moons that should be dead but are not. The featureless billiard ball turned out to be one of the most complex worlds in the solar system. Every model, built over 4 decades, started from a single flyby that arrived at the worst possible moment and looked through the wrong wavelength of light. You and I inherited a version of this planet that never existed. What JWST found changes Uranus and redefines what a typical planet looks like across the galaxy. Ice giants are the most common type of world out there. We barely understood the one in our own backyard. The evidence spans diamond rain, impossible water, a magnetic field that defies every model, and a moon that no longer exists. The trail starts with the only spacecraft that ever visited Uranus, a machine that flew 2 billion miles and arrived at exactly the wrong time. On December 18, 2023, the James Webb Space Telescope pointed its 6.5-meter mirror at Uranus and took a single wide-field infrared exposure. The image came back with 11 of 13 known rings, 14 moons, storm systems, a glowing polar cyclone, and behind it all, galaxies billions of light years away. They photobombed the frame like they had nowhere else to be. This was the most detailed portrait ever captured of the 7th planet, and it looked nothing like the planet scientists thought they knew. For 37 years, the only close-up of Uranus came from Voyager 2. That spacecraft flew past in January 1986 and sent back images of a smooth, pale, blue-green sphere. No storms, no visible features, no drama. Textbooks printed those images for decades and described Uranus as the boring planet, a featureless billiard ball rolling through the outer solar system on its side at 97.77 degrees of axial tilt. The Webb telescope destroyed that description in a single exposure, but the image did more than reveal a pretty planet. It opened a series of problems that planetary science still cannot close. Voyager 2 measured something about the magnetosphere of Uranus during that 1986 flyby, something that would mislead researchers for nearly 4 decades. The magnetic field data became the foundation for every model built since, and every one of those models may have been built on a freak accident. There is a moon missing from this system, not a moon we have failed to find, a moon that no longer exists. Its absence may explain why Uranus is tilted so far on its axis, but confirming that requires evidence we do not yet have. The effective temperature of Uranus is 59 Kelvin, about -356 degrees Fahrenheit. It is the coldest planetary atmosphere in the solar system, colder than Neptune despite being 1 billion kilometers closer to our star. And yet the upper atmosphere registers at 850 Kelvin, roughly 577 degrees Celsius. Both measurements are real. No model accounts for the second one. Webb showed something else in the Uranian system, a tiny object orbiting between 2 known moons that Voyager 2 flew directly past and missed entirely. It had been there the whole time, circling in one of the most photographed regions of the system, invisible to cameras that lacked the sensitivity to see it. Deep inside this planet, under pressures that exceed 200 gigapascals, water exists in a form that breaks the categories we use to describe matter. It is solid and liquid at the same time, electrically conductive, and possibly responsible for generating one of the strangest magnetic fields in the solar system. Every one of these problems traces back to the same fundamental question: what is Uranus? And why has every attempt to answer that question given us the wrong answer? The trail starts with the only spacecraft that ever visited, a machine that arrived at exactly the wrong moment, looked through exactly the wrong instruments, and gave us a picture of Uranus that we believed for almost 4 decades. Voyager 2 launched in 1977 on a trajectory that would carry it past Jupiter, Saturn, Uranus, and Neptune, a grand tour made possible by a planetary alignment that occurs once every 175 years. By the time it reached Uranus on January 24, 1986, the spacecraft had already been flying for 8.5 years. Voyager 2 made its closest approach at 81,500 kilometers, roughly the distance from New York to Los Angeles 30 times over. The spacecraft had about 5 to 6 hours of close imaging before the planet shrank behind it. In that window, Voyager captured more than 7,000 photographs, discovered 11 moons and 2 rings, measured the magnetic field, sampled the magnetosphere, and recorded ultraviolet emissions. By any reasonable standard, the flyby was a technical triumph. Every instrument performed. The problem was timing. Uranus takes 84 Earth years to orbit our star. Its axial tilt of 97.77 degrees means the planet essentially rolls around its orbit on its side. During solstice, one pole points almost directly at the central star, while the other faces deep space. Voyager arrived during southern summer solstice. The South Pole was aimed at our star. The entire northern hemisphere sat in darkness, turned away, unobservable. Voyager could only photograph half a planet. That alone would have been limiting. But the cameras made it worse. Voyager 2 carried imaging systems designed in the early 1970s, optimized for visible light. These cameras worked beautifully at Jupiter, where cloud bands and storm systems create vivid contrast in optical wavelengths. They worked at Saturn, where ring shadows and atmospheric features pop in visible light. At Uranus, visible light showed almost nothing. Methane in the upper atmosphere absorbs red wavelengths and scatters blue, creating a uniform blue-green haze that masks everything beneath it. Storms were there. Cloud features were there. Voyager simply could not see them. The images that came back to the Jet Propulsion Laboratory in Pasadena showed a smooth, featureless disk. Image processing made it look even duller. The pale blue sphere was published in every textbook, every encyclopedia, every popular science book for the next 2 decades. Scientists drew a reasonable conclusion from the data they had. Uranus was atmospherically dead, geologically quiet, the least interesting giant planet. That conclusion shaped funding decisions, mission priorities, and research focus for 37 years. When space agencies debated where to send the next probe, Uranus ranked low because there seemed to be nothing to find. When graduate students chose research topics, Uranus offered little. The boring planet became a self-fulfilling prophecy. Nobody looked because nothing seemed to be there, and nothing seemed to be there because nobody looked. The handful of scientists who kept studying Uranus through ground-based telescopes knew the picture was incomplete. Heidi Hammel, who had worked on the Voyager encounter as a graduate student, continued monitoring the planet for years afterward. She believed the featureless appearance was an artifact of the tools and the timing. She was right, though it would take nearly 2 decades for the planet to prove it. But the cameras were only half the story from that flyby. Voyager 2 carried a magnetometer, an instrument designed to map magnetic fields. As the spacecraft swept past Uranus, the magnetometer recorded a magnetic field tilted 59 degrees from the planet's rotation axis and offset from the center by about 1/3 of the planetary radius. By any standard in planetary science, this was bizarre. Earth's field is tilted about 11 degrees, Jupiter's about 10. Uranus appeared to be a magnetic oddball, and the readings from that single pass became the foundation for every magnetic model of the planet, built over the next 4 decades. The magnetometer worked perfectly. The readings were accurate. But what Voyager measured that day was shaped by something the mission team did not know was happening. something that occurs roughly 4% of the time in the space around Uranus. Here is what happened. As Voyager 2 passed through the Uranian magnetosphere on January 24, 1986, the solar wind was in an unusual state. A compression event, a surge of charged particles from our star, had squeezed the magnetosphere to a fraction of its typical size. Think of it as measuring the size of a balloon while someone is sitting on it. The magnetometer recorded real data, accurate data, but the data captured a compressed, distorted version of the magnetic environment, one that bore little resemblance to its normal configuration. This compression event is not common. Analysis of solar wind conditions suggests it occurs roughly 4% of the time at Uranus's distance from our star. Voyager happened to fly through during that 4% window. One flyby, one measurement. And that measurement became the basis for every magnetospheric model published between 1986 and 2024. The models described a magnetosphere that was relatively small and structurally simple. Odd, yes, because of the 59-degree tilt and the offset from center, but manageable. The kind of magnetic environment that could be explained with straightforward physics and a slightly unusual internal structure. Researchers built simulations, published papers, refined parameters. An entire subfield of planetary magnetism grew up around readings taken during a statistical anomaly. The equivalent would be studying a city's traffic patterns by observing them during a hurricane and calling the result normal. The data is real. The instruments were accurate. The conclusion is wrong because the conditions were exceptional and nobody knew it at the time. It took decades for the problem to surface. Ground-based observations could not directly measure the magnetosphere from nearly 2 billion miles away. Indirect methods hinted that something was off, but the Voyager data carried enormous authority. It was the only direct measurement. Challenging it required either a new mission or a fundamentally different observing approach. The James Webb Space Telescope provided that different approach. In January 2025, Webb's near-infrared spectrograph stared at Uranus for 15 continuous hours, nearly one full Uranian day of 17 hours and 14 minutes. The observation was led by Paola Tiranti, a doctoral researcher at Northumbria University, under a program directed by Henrik Mellin, designated number 5073. The target was not the planet's visible surface. Webb tracked emissions from a specific ion called H3+, trihydrogen cation, a molecule that glows in infrared when energized by charged particles. By mapping where H3+ was emitting and at what intensity, the team built the first three-dimensional map of the Uranian ionosphere, extending up to 5,000 kilometers above the cloud tops. What they found was auroral bands, structured, glowing regions where charged particles from the magnetosphere interact with the upper atmosphere, active, complex, dynamic, structured in ways nobody expected. This was the opposite of the quiet, simple magnetic environment the Voyager-era models described. 39 years of magnetospheric science at Uranus rested on a single pass through a compressed field during a 4% probability event. The models built on that pass described a system that the Webb telescope now showed did not exist. The real magnetosphere of Uranus is larger, more active, and more structurally complex than any model published before 2025. So Voyager got the surface wrong because it looked invisible light during solstice, and it got the magnetic field wrong because it arrived during a freak solar wind compression. Two instruments, two wrong conclusions, both from the same flyby. But there was something even more fundamental that the 1986 data could not have revealed. Something about what Uranus is actually made of at the molecular level. For decades, the textbook description of giant planet atmospheres followed a simple rule. All four giant planets, Jupiter, Saturn, Uranus, and Neptune, had ammonia-dominated upper cloud layers. The chemistry varied by depth and pressure, but at the cloud tops, ammonia was king. This made intuitive sense. Ammonia is abundant in the outer solar system. Jupiter's cloud tops reek of it. Saturn's do too. The assumption extended naturally to the ice giants farther out. In April 2018, Patrick Irwin at the University of Oxford published a paper in Nature Astronomy that broke that assumption apart. His team used the near-infrared integral field spectrometer on the Gemini North Telescope, an 8-meter instrument perched at the summit of Mauna Kea in Hawaii, nearly 14,000 feet above sea level. They pointed it at Uranus and detected hydrogen sulfide dominating the upper cloud deck at concentrations between 0.4 and 0.8 parts per million. Hydrogen sulfide, the compound that gives rotten eggs their smell. This was not a minor compositional tweak. Ammonia versus hydrogen sulfide represents fundamentally different formation conditions in the early solar system. Jupiter and Saturn formed close enough to our star to retain ammonia in their upper atmospheres. The temperatures and pressures in their formation zones favored nitrogen compounds. Uranus and Neptune formed in colder, more distant regions where sulfur-rich compounds dominated. One spectroscopic detection rewrote the formation history of two planets. The finding also explained something Voyager could never have resolved. Hydrogen sulfide clouds behave differently from ammonia clouds. They form at different pressures, have different optical properties, and interact with sunlight in different ways. Some of the atmospheric features that appeared absent in Voyager's visible light images may have been hidden by the specific optical behavior of hydrogen sulfide hazes rather than truly missing. Irwin's detection required ground-based infrared spectroscopy at a level of precision that did not exist in 1986. Voyager's instruments were not designed to distinguish between ammonia and hydrogen sulfide at cloud-top concentrations. The mission never had a chance to catch this. But the result meant that the standard atmospheric model taught in every planetary science course for 30 years was wrong for half the giant planets in our solar system. If Uranus formed in a different chemical environment than Jupiter and Saturn, the differences should not stop at the clouds. They should run deeper, through the atmosphere, through the mantle of pressurized ices, all the way to whatever sits at the center. And they do. The interior of Uranus contains material that defies the categories physicists use to describe matter. Roughly 60% of Uranus, by mass, consists of water, ammonia, and methane. But at the pressures inside this planet, hundreds of gigapascals, none of those substances exist in any form you would recognize. Water does not remain liquid. It does not freeze into ordinary ice. Under the crushing weight of an atmosphere that extends thousands of miles deep, water molecules are forced into an arrangement that has no equivalent on Earth's surface. The oxygen atoms lock into a rigid crystalline lattice, a solid framework, but the hydrogen atoms break free from their molecular bonds and flow through that lattice like a liquid, solid and liquid at the same time. Physicists call this state superionic ice. It was predicted by theory in the 1980s. It was confirmed in laboratories at Lawrence Livermore National Laboratory under conditions that simulate the Uranian interior, and it may be the key to the most persistent mystery about this planet's magnetic field. Superionic ice is electrically conductive. The free-flowing hydrogen atoms carry charge as they move through the oxygen lattice and create a medium that can sustain electrical currents. This matters because magnetic fields in planets are generated by dynamos, convective motion of conductive fluid that converts kinetic energy into magnetic energy. On Earth, the dynamo operates in the liquid iron outer core. On Jupiter and Saturn, it operates in layers of metallic hydrogen compressed under enormous pressure. For decades, the assumption was that Uranus must have something similar. A metallic or highly conductive region deep in the interior, probably near the core, generating the magnetic field the way Earth's core generates ours. The models place the dynamo deep, analogous to other planets. The problem is that the magnetic field of Uranus does not behave like a deep core dynamo should produce. The 59-degree tilt from the rotation axis and the 1/3 radius offset from center are extreme. Earth's magnetic field is roughly dipolar, a clean north-south alignment generated by organized convective flow in the core. Uranus produces a field that is multipolar, messy, and tilted so far that the magnetic poles sit closer to the equator than to the geographic poles. Superionic ice changes the picture entirely. If the electrically conductive layer sits distributed through the thick, icy mantle, instead of deep in a metallic core that makes up most of the planet's volume, the dynamo operates in a fundamentally different geometry. The convective patterns that generate the field would be broader, shallower, and more chaotic than a core-based dynamo. The 59-degree tilt and the offset stop being anomalies. They become exactly what you would expect from a mantle-based dynamo driven by superionic water. This is not theoretical speculation about a hypothetical substance. Researchers at Lawrence Livermore used high-powered lasers to compress water samples to pressures exceeding 100 gigapascals and temperatures above 2000 Kelvin. The water transformed into superionic ice. They measured its electrical conductivity. The numbers matched what models require to sustain a planetary dynamo. Scientists created the material that likely fills most of Uranus, held it for fractions of a second in a laboratory, and confirmed that it conducts electricity. The magnetic field of Uranus is generated in a way that has no parallel anywhere else we have studied up close. Earth, Jupiter, Saturn, Mercury, each has a metallic region producing a roughly organized field. Uranus produces its field in an ocean of water that is simultaneously crystalline and fluid. The field that results is tilted, offset, and possibly unstable. Some models suggest it may wander over time, never settling into a fixed orientation, but superionic ice is not the only exotic material existing under those pressures. There is something else precipitating through this impossible ocean, something that may interact with the superionic water to influence the dynamo itself. Scientists did not just predict this second material, they made it in a laboratory. In 2017, at the SLAC National Accelerator Laboratory in Menlo Park, California, a team led by Dominic Krauss pointed one of the most powerful X-ray lasers on Earth at a sample of polystyrene, a stand-in for the carbon-hydrogen compounds found inside ice giants. They compressed it to conditions matching the deep interior of Uranus. Carbon atoms separated from the hydrogen, and they reassembled into diamond. The diamonds that form inside Uranus are not gemstones. They are nanodiamonds. At first, tiny crystalline structures nucleating under pressures that exceed 200 gigapascals at temperatures of thousands of degrees. But they do not stay small. Over millions of years, as they precipitate downward through the surrounding medium, they grow. Some models suggest they could reach enormous sizes, though the exact dimensions depend on variables that laboratory experiments cannot fully replicate. What Krauss and his team demonstrated at SLAC in 2017 was proof of concept. They created nanodiamonds from hydrocarbon material under simulated ice giant conditions. The diamonds formed. They were real. They were measurable. In 2024, experiments at the European X-ray Free Electron Laser Facility in Hamburg refined the result further. Diamond formation begins at lower pressures than the original models predicted. That means the diamond rain zone inside Uranus starts shallower in the planet than anyone had calculated. The process is more extensive than the first estimates suggested. Picture what this means physically. Thousands of miles below the visible cloud tops, in a region where pressure would crush any structure humans have ever built, carbon atoms pulled from methane molecules are snapping into crystalline lattices and falling through superionic water, that impossible solid-liquid hybrid, sinking deeper into the planet under their own weight. Diamond rain is not a metaphor. It is a literal description of a physical process happening continuously inside the seventh planet from our star. The falling diamonds do something important as they sink. They release gravitational potential energy as heat. They also create compositional gradients in the surrounding material. Diamond-enriched fluid is denser and sinks. Diamond-depleted fluid is lighter and rises. This sets up convective circulation, exactly the kind of motion a dynamo needs. In a medium that is already electrically conductive, thanks to the superionic water, this convection can generate and sustain magnetic fields. The connection is direct. Diamond rain may not just be an exotic curiosity inside Uranus. It may be one of the driving forces behind the planet's magnetic field. The 59-degree tilt, the 1/3 radius offset, the multipolar structure, all of these features could be signatures of a dynamo, powered at least partly by carbon precipitation through a superionic ocean. No other planet we have studied up close has anything like this mechanism. But even with superionic ice and diamond rain established in laboratories, the interior of Uranus remained a model, an inference, a set of calculations supported by physics experiments but never directly observed. What scientists needed was a way to see the magnetic field's behavior from the outside, to look for signatures that would confirm or deny the mantle dynamo hypothesis. Voyager's single compressed measurement was useless for this purpose. Ground-based telescopes lacked the sensitivity. And then the Webb telescope stared at Uranus for 15 straight hours and mapped the invisible. The auroral data from January 2025 did more than confirm that the magnetosphere was active. The structure of the auroral bands carried information about the geometry of the magnetic field, producing them. Auroras trace the paths where charged particles funnel down along magnetic field lines and collide with atmospheric molecules. The pattern of the auroras maps the architecture of the field itself. What Tiranti and Melin's team found was complexity. The auroral bands followed patterns consistent with a field that is multipolar, possibly unstable, and operating nothing like the tidy dipole models predicted from Voyager's single pass. The 15-hour observation from January 2025 was not just long by space telescope standards, it was strategic. Uranus rotates once every 17 hours and 14 minutes. 15 hours of continuous coverage captured nearly a full rotation, allowing the team to build a three-dimensional picture of the ionosphere as different longitudes rotated into view. No one had ever attempted anything like this for Uranus. Every previous measurement of the upper atmosphere came from ground-based telescopes peering through Earth's own atmosphere, fighting turbulence and water vapor to detect faint infrared signals from a world nearly 2 billion miles away. The resulting map extended from the cloud tops to 5,000 kilometers above the visible surface, with ion density peaking at roughly 1,000 kilometers altitude. The map was built from emissions of H3+, trihydrogen cation, the same molecule Tiranti and Melin's team had targeted for the auroral study. H3+ forms when energetic particles ionize hydrogen molecules in the upper atmosphere. It glows in infrared, and the intensity and distribution of that glow carries information about temperature, density, and energy input at every point in the ionosphere. The auroral bands showed up clearly, structured, persistent, following magnetic field lines down into the atmosphere at specific latitudes. These were not faint hints. The emissions were strong enough that the team could track how they shifted as the planet rotated, building a picture of which longitudes showed stronger magnetic interactions and which showed weaker ones. The pattern was consistent with a magnetic field far more complex than the simple tilted dipole that Voyager-era models described. For 37 years, the working assumption had been that Uranus's magnetosphere was relatively quiet, active enough to exist, yes, but lacking the dramatic auroral displays seen at Jupiter and Saturn. The Voyager magnetometer data, taken during the compression event, reinforced this picture. A squeezed magnetosphere looks less active than an expanded one. The models built on that data predicted minimal auroral emission, minimal energy transfer from the magnetosphere to the atmosphere, a quiet upper atmosphere receiving little from above. The Webb data contradicted every part of that prediction. The auroral bands were active. The magnetic interactions were complex. Energy was flowing from the magnetosphere into the ionosphere along structured pathways. The 37-year-old picture of a magnetically quiet Uranus was not incomplete. It was wrong. The average temperature across the mapped ionosphere registered at 426 Kelvin. The peak hit 470 Kelvin at an altitude of 3,625 kilometers. Both numbers were significant. Both were lower than expected. Previous ground-based estimates had placed the ionospheric temperature considerably higher, and every seasonal model predicted the numbers should be climbing as solstice approached. Instead, they were falling. The auroral bands were dumping energy into the upper atmosphere, but the atmosphere was colder than it should have been. The aurora was real. The energy transfer was measurable, and yet the temperature was declining. The Webb team had mapped an active, complex ionosphere that was somehow losing heat while gaining energy. This was not a small discrepancy buried in error bars. The cooling trend extended back more than 3 decades through independent ground-based datasets. The auroral data contained a contradiction that went beyond magnetic field models, one that challenged basic physics intuition about how planets behave as they approach their star. Uranus is approaching its northern summer solstice, expected in 2028. The North Pole is slowly turning toward our star for the first time since 1944, before the space age, before radio telescopes could study planets, before humanity had any tool capable of observing this event. Basic thermodynamics makes a straightforward prediction. As a hemisphere tilts toward its energy source, the upper atmosphere should absorb more energy and warm up. This prediction works on Earth. It works on Mars. It works on Jupiter and Saturn. It does not work on Uranus. Ground-based measurements going back to the early 1990s showed the thermosphere temperature declining. The trend was clear, but the data was noisy. Atmospheric seeing, calibration uncertainties, and the sheer difficulty of measuring temperatures on a world nearly 2 billion miles away left room for doubt. The Webb telescope eliminated that doubt. 426 Kelvin average, lower than every previous measurement taken by any instrument. The cooling is real. It has persisted for more than 30 years. And it is moving in the opposite direction from what every thermal model predicts. The thermosphere had been measured at 800 to 850 Kelvin in earlier decades. That number was already a paradox. The effective temperature of the planet, the temperature its surface radiates at, is 59.1 Kelvin, negative 356 Fahrenheit. The coldest planetary atmosphere in our solar system, colder than Neptune, a planet that orbits roughly 1 billion kilometers farther from our star. The gap between the surface and the upper atmosphere, from 59 Kelvin to 850 Kelvin, has no accepted explanation. On Jupiter and Saturn, auroral heating accounts for most of the upper atmospheric warmth. Charged particles from powerful magnetospheres slam into the atmosphere and deposit energy. The Webb telescope just proved that Uranus has active auroral bands too. Energy is flowing into the ionosphere along structured magnetic pathways. And yet, the temperature is dropping. The aurora is there. The energy source is there. The heating is not. Other candidates have been proposed over the years. Gravity waves propagating upward from the lower atmosphere, could deposit energy at higher altitudes. Chemical reactions at high altitudes could release thermal energy. Bombardment by charged particles from the solar wind could heat the thermosphere directly. Each candidate falls short by orders of magnitude when the energy budgets are calculated. The numbers do not close. The energy required to maintain 850 Kelvin in the thermosphere exceeds what any known mechanism can deliver. And now that temperature is declining anyway, making the accounting even harder. So the upper atmosphere is inexplicably hot, and it is getting colder for no apparent reason. A planet approaching our star is losing thermal energy from its upper atmosphere while maintaining a surface temperature that already defies explanation. Webb's auroral discovery made the problem worse, not better. Finding the energy source should have helped. Instead, it revealed that the energy is arriving, and the heating is still not happening. Whatever is controlling the temperature of the Uranian upper atmosphere operates by rules that current physics does not describe. The cooling mystery connects to something older and deeper, a problem that separates Uranus from every other giant planet in the solar system and has resisted every attempt at explanation for decades. Jupiter radiates about 1.7 times the energy it absorbs from our star. Saturn radiates roughly 1.8 times. Neptune, despite orbiting farther from the central star than any other planet, radiates 2.61 times its absorbed solar energy. These planets are all generating substantial internal heat, leftover thermal energy from their formation 4.5 billion years ago, slowly leaking outward through their atmospheres. Uranus radiates between 1.06 and 1.15 times its absorbed energy, almost nothing. For a planet of its size and mass, 14.5 times Earth, this number is difficult to explain. Uranus should have residual formation heat. It should have gravitational contraction releasing energy. The models that work for Jupiter, Saturn, and Neptune predict that Uranus should be glowing with internal warmth. It barely registers. Two explanations dominate the literature. The first proposes that something inside Uranus is blocking the heat from escaping. A compositional boundary layer, deep in the interior, perhaps created by a mixing gradient between the hydrogen-helium envelope and the icy mantle, could act as thermal insulation. Heat exists below the barrier, but cannot conduct or convect its way to the surface. The planet is hot on the inside and frozen on the outside, separated by a wall of its own chemistry. The second explanation is more violent. Something destroyed the heat reservoir entirely. Early in the solar system's history, when planets were still forming and giant impacts were common, a collision could have stripped away or redistributed the thermal energy that Uranus should have retained. If enough heat was expelled during the impact, the planet would have started its post-formation life colder than its siblings. 4.5 billion years later, the deficit would still show. Both explanations point to the same suspect, the 97.77 degree axial tilt. Something knocked this planet on its side. Something massive. Something energetic enough to reorient an entire world that masses 14.5 times what Earth does. That event, whatever it was, is the most likely candidate for both the tilt and the thermal anomaly. The leading hypothesis has been a giant impact, a body roughly the mass of Mars or larger, striking Uranus during the chaotic early period of solar system formation, could have tipped the planet over and ejected enough thermal energy to explain the missing heat. Simulations support this. The physics works. The energy budget closes, but a single giant impact creates a problem that sits right at the center of the Uranian system, visible in the orbits of its 29 known moons. If a Mars-sized body slammed into Uranus hard enough to tilt it 97 degrees, the impact should have dramatically altered the planet's spin and left debris in orbits that do not match what we see. Specifically, a single massive collision should have scattered the moons into retrograde orbits, moving opposite to the direction of the planet's rotation. Every one of the 27 moons known before 2025 orbits prograde in the same direction Uranus spins. Their orbits are neatly aligned with the planet's tilted equatorial plane, as if they formed after whatever event caused the tilt, or were somehow carried along with it. A single giant impact does not easily produce this arrangement. The contradiction between the tilt and the moons has driven researchers to look for alternatives. Rogoshinsky and colleagues developed a hypothesis that replaces the single catastrophic impact with something slower, stranger, and in some ways more disturbing. Imagine a massive moon, far larger than any that currently orbits Uranus, forming in the early days of the system from the same disk of material that built the other satellites. This moon would have been gravitationally significant, large enough to interact with the planet's spin axis through a process called secular spin-orbit resonance. Over hundreds of millions of years, the gravitational tug of this moon, combined with orbital mechanics involving the outer planets, could have gradually torqued Uranus's axis away from vertical, slowly, degree by degree, over timescales that make geological processes look rushed. The math supports it. Rogoshinsky's models show that a moon with the right mass in the right orbit could tilt Uranus to its current 97.77 degrees without requiring any impact at all. The prograde moons remain prograde because there was no sudden, violent event to scatter them. The tilt accumulated gradually while the rest of the system adapted, but the model requires that moon to be gone. As the resonance process played out, the moon's orbit would have evolved. Tidal interactions with Uranus would have caused it to spiral inward over time. Eventually, the moon would have crossed the Roche limit, the distance at which the planet's tidal forces exceed the gravitational forces holding the moon together. Inside that boundary, the moon would have been torn apart, shredded into fragments. Some of those fragments may have formed a temporary ring. Some may have been absorbed into the planet. Some may have accreted into smaller moons. The ghost moon tilted its planet over hundreds of millions of years, then was destroyed by the very gravitational forces it had been dancing with. The evidence for this moon is circumstantial. The tilt itself, the prograde orbits of the existing moons, the missing internal heat, which could have been redistributed during the long resonance process, the orbital characteristics of the inner moons, which show patterns that could be remnants of a disrupted larger body. Each piece of evidence is ambiguous on its own. No single observation confirms the ghost moon existed, but together, they outline something that happened billions of years ago, something catastrophic played out in slow motion. There is a version of the hypothesis that combines both ideas. A large impact struck Uranus, partially tilting it and providing the initial perturbation. Then a massive moon, possibly formed from impact debris, completed the job through resonance over geological time before being consumed. This hybrid model addresses more of the observational constraints than either hypothesis alone, but it is also harder to test because it requires two events rather than one. Whether impact or ghost moon or both, one conclusion is unavoidable. Something violent happened to Uranus in the deep past, something that altered its axis, possibly drained its heat, and shaped the system we observe today. The Webb telescope cannot look backward in time to see what happened billions of years ago, but it found evidence that the consequences of that ancient violence extend beyond the planet itself, reaching all the way to the moons. The damage is still visible on their surfaces. The damage is visible on 5 of them: Ariel, Umbriel, Titania, Oberon, and Miranda. For decades, planetary scientists classified all 5 as dead. Frozen rocks drifting in the outer solar system, too far from any heat source, too small to retain internal energy, too old to have anything interesting happening beneath their surfaces. Textbooks printed this as fact. Mission proposals to Uranus ranked the moons as secondary targets because the consensus said there was nothing to find. Then, in 2024, Webb's near-infrared spectrograph pointed at Ariel, the 4th largest of Uranus's moons, and recorded something that should not exist on a dead world: carbon dioxide ice, more than 10 millimeters thick on Ariel's trailing hemisphere. That measurement alone would have been notable. Carbon dioxide ice on an airless body is inherently unstable. Solar radiation breaks it apart. Charged particles from the magnetosphere sputter it away. Over geological timescales, any carbon dioxide deposited on a surface like Ariel's should vanish. 10 millimeters is not a trace. It is a reservoir, and it was not alone. The spectrograph also detected carbon monoxide, ice, and carbonate minerals embedded in the surface. The combination of all three pointed in one direction. Something beneath Ariel's crust is pushing material to the surface. The technical term is cryovolcanism. Instead of molten rock, the eruptions involve water, ammonia, or carbon dioxide forced upward from a liquid layer below the ice shell. For cryovolcanism to work, there has to be liquid down there. Ariel, a moon 472 kilometers across orbiting a planet nearly 3 billion kilometers from our star, likely has a subsurface ocean. This is not a tentative suggestion buried in a footnote. The Webb team flagged all 5 major Uranian moons as potential ocean worlds. The carbon dioxide detection on Ariel was the thickest measurement of that compound on any airless body in the solar system. The carbonates require liquid water to form. The carbon monoxide requires an energy source to sustain it against breakdown. Every line of evidence converges on the same conclusion. These moons are geologically active. Right now, at this moment, the implications reach beyond Uranus. Before this detection, the known ocean worlds in the solar system were Europa, Enceladus, Titan, and possibly Ganymede and Callisto. All of them orbit Jupiter or Saturn, where tidal heating from their massive parent planets provides the energy to keep water liquid. Uranus is smaller. Its gravitational influence is weaker. The fact that its moons might harbor oceans suggests the conditions for subsurface liquid water are far more common than anyone assumed. And the timing matters. Voyager 2 flew past these same moons in 1986. Its cameras captured their surfaces in visible light at moderate resolution. The images showed craters, some geological features on Ariel and Miranda, and not much else. For 38 years, those images defined the moons. Nobody had reason to look deeper because the pictures said there was nothing deeper to find. Webb did not take better pictures. It looked at a completely different kind of light. Wavelengths where molecular signatures reveal themselves, where carbon dioxide and carbon monoxide and carbonates announce their presence through absorption features invisible to any camera Voyager carried. The moons had been speaking the entire time. We had been listening on the wrong frequency. Ariel was not the only member of the Uranian system hiding in plain sight. Webb's sensitivity reached further than any previous instrument pointed at this region of the solar system, and it found something even Voyager's cameras should have caught. On February 2nd, 2025, the Webb telescope discovered a new moon orbiting Uranus. The object, designated S/2025 U1, is roughly 10 kilometers across. It circles the planet between the orbits of Ophelia and Bianca, 2 small inner moons that shepherd the Epsilon ring. The discovery brought the official count to 29, but the number is less important than the location. Voyager 2 flew directly through this region in 1986. The spacecraft passed within 81,500 kilometers of Uranus and spent its closest hours photographing the inner ring system and the moons embedded within it. Voyager discovered 11 moons during that flyby. It mapped the rings. It built the census that planetary scientists used for the next 4 decades. And it flew right past a 10-kilometer object without detecting it. The miss was not a failure of the mission. Voyager's cameras had finite resolution at the distances involved, and the spacecraft was moving fast. Objects below a certain size threshold were simply invisible to its instruments. But the fact remains, one of the most photographed regions of the Uranian system contained a moon that went undetected for 39 years. The inner ring region is not empty space. It is crowded with particles, dust, and apparently more solid bodies than anyone catalogued. The question this raises is straightforward. If a 10-kilometer moon was hiding between Ophelia and Bianca, how many others are there? Webb found this one because it happened to be looking with the right instrument at the right time with enough sensitivity. The telescope was not conducting a dedicated moon search. S/2025 U1 appeared in data collected for other purposes. A systematic survey of the Uranian ring system with Webb's capabilities has never been performed. The 29 moons we know about are almost certainly not the final number. This matters for the rings themselves. Uranus has 13 known rings, and their structure depends on gravitational interactions with nearby moons. The Epsilon ring, the brightest and most prominent, is kept narrow by Ophelia and Cordelia, acting as shepherd moons. Their gravity confines ring particles into a tight band. Other rings show features that suggest additional gravitational influences, wakes and gaps, and density variations that do not match the known moon population. Every undiscovered moon is a missing variable in the equations that describe ring dynamics. The system is more complex than its inventory suggests. The discovery also illustrates a broader pattern in this investigation. Voyager 2 arrived at Uranus with the best technology available in 1986 and built the most complete picture it could. That picture became the baseline. Every textbook, every model, every assumption about the Uranian system was built on it. And piece by piece, new instruments are revealing that the baseline was incomplete. The magnetosphere was measured during a freak compression event. The atmosphere was photographed in the wrong wavelength. The moons were classified as dead because nobody could see the carbon dioxide. And the moon census missed objects that were physically there the entire time. S/2025 U1 is 10 kilometers of rock and ice. It has no atmosphere, no geological features of note, no obvious scientific importance on its own. But its existence proves that our inventory of the Uranian system is not finished. It proves that even the parts of the system Voyager studied most closely still contain surprises, and it connects to something JWST revealed about the rings themselves, features that Voyager's visible light cameras could detect but could never fully explain. Voyager 2 detected 11 rings around Uranus in 1986. 2 more were identified later through ground-based stellar occultation measurements, bringing the total to 13. The rings are thin, dark, and narrow compared to Saturn's brilliant ice bands. In visible light, they appear as faint lines against the blackness of space. Voyager's cameras captured them well enough to establish their basic geometry, but the images lacked the resolution and wavelength coverage to reveal what the rings are actually doing. Webb changed that in February 2023. The telescope's near-infrared camera captured 11 of the 13 rings in a single exposure, including the Zeta ring, a diffuse inner structure so faint that ground-based telescopes could barely detect it. The December 2023 wide-field image pushed the detail further. In infrared wavelengths, the rings told a different story than they had in visible light. The brightness profiles shifted. Ring particles that appeared uniform in Voyager's images showed variation in infrared, suggesting differences in composition or size distribution across different sections of the same ring. The Epsilon ring, which Voyager had mapped as a relatively simple structure confined by Ophelia and Cordelia, displayed fine-scale features consistent with gravitational wakes. These are density waves created when a nearby mass pulls on ring particles as it passes. The wakes in the Epsilon ring do not all correspond to known shepherd moons. Some of them point to gravitational sources that have not been identified. The Zeta ring itself is a puzzle. It sits interior to all the other rings, closer to the planet, and it is broad and diffuse where the others are narrow and defined. Its particle population appears to be dominated by small grains, dust-sized material that should not survive long in that orbital environment. Radiation pressure, plasma drag from the magnetosphere, and gravitational perturbations should sweep small particles out of stable orbits on timescales of thousands of years. For the Zeta ring to exist in its current state, something must be replenishing it. Collisions between unseen bodies, meteoroid impacts on small moons, or some ongoing process that feeds dust into the ring faster than it gets removed. This is the same pattern that appeared with Ariel's carbon dioxide, a feature that should be temporary, that should have disappeared by now, that requires an active process to sustain it. The Uranian system is not a static arrangement of ancient leftovers. It is a dynamic environment where things are happening right now. The rings also interact with the magnetosphere in ways Voyager could not observe. Charged particles trapped in the magnetic field sweep through the ring plane, eroding ring particles and creating plasma. The geometry is unusual because the magnetic field is tilted 59 degrees from the rotation axis, so the field sweeps across the rings at an angle that changes as the planet rotates every 17 hours and 14 minutes. Ring particles experience different radiation doses depending on their orbital position and the phase of the planet's rotation. Webb's infrared observations captured brightness variations in the rings, correlating with this geometry, suggesting the rings are being actively processed by the magnetic field. Voyager showed us that Uranus had rings. Webb is showing us that those rings are alive, sculpted by moons we have not found, sustained by processes we are still identifying, and interacting with a magnetosphere that was itself mischaracterized for nearly 4 decades. But the rings were not the most dramatic surface Webb examined in the Uranian system. That distinction belongs to the smallest of the 5 major moons and the most violent landscape in the known solar system. Miranda is 472 kilometers across. It is the smallest of Uranus's 5 major moons, barely large enough for its own gravity to pull it into a roughly spherical shape. Voyager 2 photographed Miranda during the 1986 flyby, and the images were confusing. The surface is a patchwork of completely different terrain types, jammed together with no coherent pattern. Smooth plains sit next to heavily cratered regions. Deep grooves cut across the landscape at sharp angles. Large oval-shaped features called coronae, 3 of them, dominate sections of the visible hemisphere. Each corona is a distinct geological province with its own texture and structure, surrounded by terrain that looks nothing like it. Miranda does not look like a single object. It looks like pieces of different objects fused together. And then there is Verona Rupes, a cliff face approximately 20 kilometers high. That makes it the tallest known cliff in the solar system, 12 times the depth of the Grand Canyon. On Miranda, where surface gravity is just 0.079 meters per second squared, a rock kicked off the edge would take roughly 12 minutes to reach the bottom. It would land at about 200 kilometers per hour, comparable to a skydiver's terminal velocity on Earth because there is no atmosphere to slow it down. The cliff exists because of tectonic forces that have no business being active on a moon this small. Something fractured Miranda's crust on a scale the moon's own internal energy should not support. Tidal heating is the leading candidate. Uranus's gravity, pulling unevenly on Miranda as it orbits, generates friction inside the moon that produces heat. Estimates put this tidal energy at 5 to 10 gigawatts. For comparison, that is roughly the output of 5 to 10 large nuclear power plants, generated continuously inside a ball of ice and rock smaller than the state of Arizona. The tidal heating would not be constant. Miranda's orbit has likely evolved over time, passing through resonances with other moons that would have amplified the heating dramatically during certain periods and reduced it during others. The coronae may represent episodes of intense internal activity when tidal forces were strongest. The heavily cratered plains may represent quieter periods when the surface had time to accumulate impacts without being resurfaced. There is a competing hypothesis. Miranda was shattered by a massive collision and then gravitationally reassembled. The pieces came back together, but not in their original arrangement, which would explain the patchwork surface. Simulations show this is physically possible for an object of Miranda's size. The evidence does not definitively favor either explanation, and both may have occurred at different points in Miranda's history. What is certain is that this tiny moon experienced forces far beyond what its size would suggest. 20-kilometer cliffs do not form on quiet worlds. Coronae with internal banding do not appear on objects with no geological engine. Miranda is a record of violence, written in ice and rock, preserved because the moon is too cold and too far from any heat source to erase the evidence. Tidal heating on Miranda, cryovolcanism on Ariel, an ocean possibly hiding beneath Titania's surface. Uranus's moons are storing and releasing energy in ways the dead moon model never predicted. But the energy has to come from somewhere, and across the entire Uranian system, the energy budget does not balance. The most extreme version of that imbalance is not on the moons at all. It is in the planet's own atmosphere, where two temperature measurements contradict each other so completely that no model can reconcile them. Uranus has an effective temperature of 59.1 Kelvin. That is negative 214 degrees Celsius, or about negative 353 degrees Fahrenheit. It is the coldest planetary atmosphere in the solar system, colder than Neptune, despite Neptune being roughly 1 billion miles farther from our star. That fact alone is strange. A planet closer to its energy source should be warmer than one farther away. Uranus breaks that rule, and nobody has a complete explanation for why. But the effective temperature measures the energy leaving the planet at the cloud tops. Higher up, in the thermosphere, the situation reverses. Measurements taken before Webb showed temperatures between 800 and 850 Kelvin. That is roughly 577 degrees Celsius, over 1,000 degrees Fahrenheit. The same planet that is the coldest in the solar system at its cloud deck is blisteringly hot in its upper atmosphere. On Jupiter, the hot thermosphere has an explanation. Jupiter's powerful auroras dump energy into the upper atmosphere, and that heat spreads globally through winds. Saturn has a similar mechanism. Charged particles spiral along magnetic field lines, slam into atmospheric molecules, and convert kinetic energy into thermal energy. Energy in, temperature up. Uranus was supposed to follow the same pattern, except its auroras were considered too weak. Before Webb, the magnetic field data from Voyager suggested a magnetosphere too feeble and too geometrically strange to drive significant auroral heating. The 59-degree tilt meant the auroral zones were in bizarre locations. The compression event meant the magnetosphere's true strength was unknown. Without strong auroras, where was the thermospheric heat coming from? Other candidates were proposed. Gravity waves propagating upward from the lower atmosphere could carry energy into the thermosphere. Charged particle bombardment from the magnetosphere could deposit heat directly. Chemical reactions in the upper atmosphere could release energy. Every candidate was modeled. Every candidate fell short. The energy deficit between what these sources could provide and what the thermospheric temperature required was not a small gap. It was orders of magnitude. Then Webb made it worse. The 2025 ionosphere observation measured an average temperature of 426 Kelvin. That is lower than every previous measurement. Ground-based observations had already detected a cooling trend beginning in the early 1990s, but Webb confirmed it with the most precise data ever collected. The thermosphere is inexplicably hot, and it is getting cooler, and the cooling is happening while Uranus approaches northern solstice in 2028, when its north pole will point directly at our star for the first time since 1944. More energy arriving at the planet, less heat in the upper atmosphere. The trend runs opposite to every prediction. This is not a question of incomplete data. Webb gave the most detailed thermal measurement of Uranus's upper atmosphere ever recorded. The cooling is real. The thermospheric heat is real. The gap between what physics predicts and what the instruments measure is real. Something about Uranus violates the energy rules that work on every other giant planet in our solar system. And this is where the investigation's parallel threads start converging. A planet with almost no internal heat emission, moons that somehow have enough energy for cryovolcanism, an upper atmosphere that is simultaneously too hot and getting colder. Every piece of the Uranian system has an energy problem. The answer might be that Uranus is not the planet we keep comparing it to. The planet it is most often grouped with, the one textbooks call its twin, turns out to be something fundamentally different. Every astronomy textbook published in the last 40 years groups Uranus and Neptune together. Ice giants, the twin planets, similar in size, similar in composition, occupying the outer edge of the solar system. Uranus has a diameter of 51,118 kilometers. Neptune is 49,528. Uranus is 14.5 times the mass of Earth. Neptune is 17 times. Both contain hydrogen, helium, and what planetary scientists call ices, meaning water, methane, and ammonia, compressed into exotic states deep in their interiors. The twin label seemed reasonable. It was also wrong. Neptune radiates 2.61 times the energy it absorbs from our star. Heat is pouring out of that planet from some internal source, probably gravitational contraction or differentiation, that is still ongoing 4.5 billion years after formation. Neptune has visible storm systems in almost every observation. The great dark spot that Voyager 2 photographed in 1989 has come and gone, replaced by other large storm features. The planet is meteorologically active at all times. Uranus radiates between 1.06 and 1.15 times. Its absorbed energy, almost nothing. For a planet of this size and age, that ratio should be much higher. Where Neptune is still releasing the heat of its formation, Uranus has either lost that heat, trapped it behind some internal boundary, or never had it in the way models predict. The two planets are the same age. They formed in the same region of the early solar system. One is thermally active, the other is thermally dead. The twin label cannot survive that difference. The atmospheres diverge under Webb's spectroscopy. Methane absorbs light at specific infrared wavelengths, and the absorption patterns differ between the two planets in ways that indicate different vertical mixing, different cloud structures, and different chemical processing. Neptune's atmosphere is well mixed, with convective circulation pulling material from depth to the surface. Uranus shows evidence of stratification, layers that do not communicate efficiently, as if something is suppressing vertical motion. The magnetospheres differ too. Both are tilted relative to their rotation axes. Neptune's field is offset by 55% of its radius, even more than Uranus's 1/3 offset. But the interaction with the solar wind produces different configurations. Neptune's magnetosphere oscillates between different geometries as the planet rotates. Uranus's does something similar but with different timing and structure, driven by its unique 97-degree axial tilt that puts the magnetic poles in completely different positions relative to the incoming solar wind. Webb is adding chemical specificity to these differences with each observation. The two planets do not have the same atmospheric composition in detail. They do not process energy the same way. They do not weather the same way. Their interior structures, as inferred from magnetic field data and gravitational measurements, follow different arrangements. Something happened to Uranus that did not happen to Neptune. The leading candidates are the ones this investigation has already examined. A giant impact, a ghost moon, some catastrophic event that altered the planet's axis, trapped its internal heat, and left it spinning on its side in a state that resembles Neptune only at the most superficial level. The twin label was a convenience. It saved textbook space. And it obscured the fact that Uranus is a unique object requiring its own explanation. The divergence between the two planets became impossible to ignore when Uranus did something Neptune does constantly, but that Uranus was never supposed to do at all. In 2004, the dead planet woke up. For nearly 2 decades after Voyager, Uranus did nothing. Ground-based telescopes with steadily improving adaptive optics turned their mirrors toward the planet and saw a calm, featureless disk. The blue-green billiard ball from 1986 held. Professional astronomers moved on to more active targets. Amateur observers rarely bothered. Uranus had been officially classified as boring by the only spacecraft to ever visit it, and the ground-based evidence confirmed the diagnosis. Then, in 2004, Uranus erupted. Over 30 bright storm clouds appeared across the planet's disk in a span of months. Heidi Hammel at the Space Science Institute and Larry Sromovsky at the University of Wisconsin tracked the systems using the Keck Observatory on Mauna Kea. The storms were not subtle. Some were visible in amateur telescopes, bright enough to punch through the methane haze that normally obscures the atmosphere in visible wavelengths. Wind speeds in the storm bands approached 900 kilometers per hour, roughly 560 miles per hour. The eruption was dramatic, unexpected, and deeply inconvenient for the dead planet model. A geologically and atmospherically inert world does not spontaneously produce 30 storm systems with extreme wind speeds. The energy required to drive those storms had to come from somewhere. Solar heating alone could not explain it because the total solar flux at Uranus's distance is minuscule compared to what drives weather on Jupiter or Saturn. Internal heat was the obvious candidate, but Uranus barely radiates more than it receives. Where was the storm energy stored? How was it released? Why did it happen in 2004 and not in 1990 or 2010? The timing offered one clue. Uranus was approaching its equinox, which occurred in 2007. During equinox, our star illuminates the planet's equator directly, and both hemispheres receive roughly equal light for the first time in decades. This seasonal transition could trigger atmospheric instabilities as temperature gradients shift and circulation patterns reorganize. But the specific mechanism connecting equinox geometry to violent storm eruption has never been pinned down. Seasonal models predict increased activity near equinox, but they do not predict explosions of this magnitude followed by relative quiet. Sromovsky's team continued monitoring through 2005 and 2006. The storms evolved. Some merged, others dissipated. New ones formed at different latitudes. The planet displayed weather patterns that, in their complexity, rivaled what Voyager had documented on Neptune. Except Uranus was not supposed to have weather, not like this. And then it faded. By the late 2000s, the violent outburst had subsided. Uranus returned to something closer to its pre-eruption state, though ground-based infrared observations continued to detect subtle features that would have been invisible to Voyager's cameras. The planet had not gone fully quiet. It had gone quiet in visible light. That distinction turned out to be everything. The 2004 eruption proved that Uranus had atmospheric energy. The question was whether the apparent quiet before and after was real or an artifact of observation. Were the storms always there, invisible at the wavelengths we were using? Or did Uranus genuinely cycle between active and dormant states? Hammel argued that improved infrared capabilities would reveal ongoing activity. Sromovsky emphasized that the 2004 event was exceptional by any measure. The debate would have continued indefinitely if not for an instrument that could settle it. Webb operated at wavelengths where Uranus's atmosphere becomes transparent in certain bands and opaque in others, creating contrast no previous telescope could achieve. What it showed was not a dead planet between eruptions. It was something else entirely. The answer had been hiding in the wavelengths. Voyager 2 carried cameras that operated in visible light, roughly the same spectrum the human eye perceives. At those wavelengths, methane in Uranus's upper atmosphere scatters and absorbs light relatively uniformly, producing the smooth blue-green appearance that became the planet's identity. Ground-based telescopes through the 1990s and early 2000s looked in visible and near-infrared bands, where the methane absorption was strong enough to mask most features below the top haze layer. The planet appeared featureless because the instruments were looking at a wavelength where featurelessness was guaranteed. Webb's near-infrared camera operates between 0.6 and 5 micrometers. Its near-infrared spectrograph covers 0.6 to 5.3 micrometers. At specific wavelengths within these ranges, methane absorbs incoming light so strongly that the upper atmosphere becomes effectively dark. Any feature below the methane layer, any storm cloud rising above it, any region where methane is depleted, appears bright against that dark background. The contrast is extreme. Features that are invisible in visible light become obvious in infrared. The February 2023 image used filters centered at 1.4 micrometers and 3.0 micrometers. At 1.4 micrometers, Webb captured the planet's atmospheric features with enough contrast to reveal cloud structures at multiple altitudes. At 3.0 micrometers, methane absorption is so deep that only the highest altitude features and ring particles remain visible. The combination produced the most detailed atmospheric portrait of Uranus ever recorded. The polar cap glowed bright white. It appears bright because methane is depleted at the North Pole, allowing the camera to see deeper into warmer atmospheric layers. This depletion pattern tells scientists that large-scale circulation is pulling methane-poor air from the interior to the surface at the poles. Uranus has a functioning atmospheric heat engine. Multiple storm features appeared at mid-latitudes, bright compact clouds that indicate convective activity punching through the methane layer. The ring system appeared in crisp detail, with 11 of 13 rings resolved. None of this was new activity. The storms, the polar cap, the ring features were all present when Voyager flew past. They had to be, because the physics driving them operates on timescales much longer than the 37 years between observations. Voyager simply could not see them. Its cameras were blind to the wavelengths where Uranus reveals itself. This realization reframes the entire history of Uranus observation. The planet was never boring. The planet was never dead. The planet was never featureless. We pointed the wrong instruments at it for 4 decades and drew conclusions from the absence of data. The billiard ball was an artifact of technology, not a property of the planet. The lesson extends beyond Uranus. Every claim about what a planet looks like depends on the wavelength of light used to make the observation. A planet that appears calm in visible light may be violent in infrared. A surface that appears smooth in one band may be fractured in another. The instrument is not a neutral window. It is a filter that determines what reality you are allowed to see. For Uranus, Webb is the first instrument that sees reality, and the reality it reveals makes Uranus scientifically essential. Because the type of planet Uranus represents is not rare, it is not unusual. Across the galaxy, planets like Uranus are everywhere, and we have exactly one close enough to study in detail. The Kepler Space Telescope, launched in 2009, stared at a single patch of sky for 4 years and counted planets. The Transiting Exoplanet Survey satellite, launched in 2018, expanded the search to nearly the entire sky. Ground-based surveys using radial velocity measurements added thousands more detections. When the census was compiled, one category dominated: sub-Neptune mass worlds. Planets in the size range between Earth and Neptune, roughly 2 to 4 times Earth's radius, with masses suggesting compositions similar to Uranus and Neptune. They are the most common type of planet discovered around other stars. Gas giants like Jupiter and Saturn are relatively rare. Rocky worlds like Earth and Mars exist in large numbers, but are harder to detect. The middle category, the ice giants, appears everywhere. Current estimates suggest billions of them in our galaxy alone. They orbit red dwarfs, yellow stars, binary systems. They appear at a wide range of orbital distances. If you chose a random star with known planets, the most likely planet you would find is something resembling Uranus, and we have almost no understanding of what these planets are like inside. Transit spectroscopy measures the thin shell of atmosphere that starlight passes through during a planetary crossing. It cannot probe the deep interior. Radial velocity gives mass, but not composition. Direct imaging is limited to young, hot worlds far from their stars. For the billions of ice giants scattered across the galaxy, the only detailed information we possess comes from two examples in our own solar system. Neptune has been studied mainly through Voyager 2's 1989 flyby and subsequent ground-based work. The data is limited. Uranus had even less until Webb arrived. Now, every observation Webb makes of Uranus directly informs the models used to interpret exoplanet data. When Patrick Irwin detected hydrogen sulfide in Uranus's clouds in 2018, that measurement changed predictions for what spectrographs should find in sub-Neptune atmospheres across the galaxy. When laboratory experiments at Lawrence Livermore confirmed superionic ice under Uranus-like pressures, that result reshaped interior models for thousands of discovered worlds. When Webb mapped the ionosphere and found complex auroral bands driven by an offset magnetic field, that data constrained dynamo models that apply to every ice giant with a tilted field. Uranus is not one planet. It is the template for a category: the hydrogen sulfide clouds, the superionic water interior, the diamond rain, the chaotic magnetic field tilted at extreme angles. If these features are typical of ice giants, then the most common type of planet in the universe has an interior filled with simultaneously solid and liquid water, a magnetic field that wanders and tilts, an atmosphere driven by sulfur compounds instead of ammonia, and a deep layer where carbon precipitates as diamond. The universe's default planet looks nothing like Earth. Understanding Uranus means understanding the architecture of planetary systems everywhere. But Webb operates from a distance of 2.87 billion kilometers. It can image the atmosphere, map the ionosphere, detect surface compounds on moons. It cannot descend into the clouds. It cannot orbit the rings. It cannot measure the magnetic field from the inside or sample the chemical composition directly. Every breakthrough in this investigation came from looking, and looking has limits. To answer the questions Webb has raised, something has to go there. In 2022, the most influential body in planetary science said exactly that. The National Academies of Sciences, Engineering, and Medicine publish a planetary science decadal survey once every 10 years. It is the document that tells NASA what missions to prioritize, what questions matter most, and where the money should go. The 2022 survey, titled Origins, Worlds, and Life, evaluated every major mission concept proposed by the planetary science community and ranked them. The number one priority for the next flagship mission was a Uranus Orbiter and Probe. The mission concept calls for a spacecraft that would launch in 2031 or 2032, using a Jupiter gravity assist to reach Uranus after a cruise of approximately 13 years. Arrival would occur around 2044 or 2045. The orbiter would carry instruments to map the magnetic field from close range, study the magnetosphere's interaction with the solar wind, image the rings and moons at high resolution over multiple years, and measure the gravitational field with enough precision to constrain interior models. The probe would separate from the orbiter and descend into the atmosphere, directly sampling chemical composition, measuring pressure and temperature profiles, and transmitting data for roughly an hour before the signal is lost. This mission would answer questions that Webb cannot. Is there superionic ice inside Uranus? The probe's atmospheric entry data, combined with the orbiter's gravity measurements, could confirm or deny the interior models. What generates the magnetic field? Close-range magnetometry over multiple orbits would map the field in 3 dimensions and reveal whether it is stable or drifting. Does Ariel have an ocean? Repeated close flybys with ice-penetrating radar could could detect subsurface liquid. Pre-formulation funding for fiscal year 2026 stands at $10 million. The mission is alive on paper, but flagship missions cost billions, and NASA's budget is under pressure from a competing priority: Mars sample return. The mission to retrieve cached rock samples from the Perseverance rover has seen its estimated cost balloon dramatically. Every dollar spent resolving Mars sample return's budget problems is a dollar unavailable for the Uranus mission. The launch window matters. The 2031 to 2032 window uses Jupiter's position to shorten the cruise time. If that window is missed, the next favorable alignment for a Jupiter gravity assist pushes the launch to the late 2030s. Arrival would not occur until the 2050s. The scientists who designed the mission, the graduate students studying Uranus today, the engineers who would build the spacecraft, all of them would be decades older. Some would have retired. Some would not be alive. Webb has transformed Uranus from the solar system's afterthought into arguably its most scientifically urgent target. Every observation since 2023 has added evidence that the planet, its rings, and its moons are active, complex, and hiding answers to questions that matter for the entire field of planetary science. The decadal survey said go. Webb said there is more there than anyone imagined. The budget says maybe, and the clock is not just ticking on the launch window. Uranus itself is approaching a moment that has not occurred since before the space age, an event that will reshape the planet's appearance and behavior in ways no human instrument has ever witnessed up close. The northern solstice arrives in 2028. Whether anyone is there to see it depends on decisions being made right now. The last time Uranus's north pole pointed directly at our star was 1944. The Second World War was still being fought. Radio astronomy barely existed. No spacecraft had left Earth's atmosphere. No human instrument recorded what happened to Uranus during that solstice because no human instrument could. 84 years later, in 2028, it will happen again. And this time, the James Webb Space Telescope will be watching. This matters because of what Voyager did not tell us. For nearly 4 decades, every model of Uranus's atmosphere, every prediction about its weather, every assumption about how its poles behave under direct illumination has been built on a single flyby that arrived at the worst possible moment in the planet's 84-year orbit. January 1986 was southern summer solstice. The entire northern hemisphere sat in darkness. Voyager's visible light cameras captured one pole baking under starlight and the other invisible. Scientists treated those images as representative. They were not. They were the equivalent of photographing Antarctica in July and concluding that Earth has no summer. The 2007 equinox offered a brief window. Both hemispheres received equal illumination for the first time since the space age began. Ground-based telescopes caught glimpses of changing cloud patterns and faint banding. But equinox is a transition, not a destination. The atmosphere was between states, shifting from one 42-year season to the next. Nobody could observe the full northern summer because it had not arrived yet. Now it is arriving. Between 2025 and 2030, Uranus's axial tilt will swing the North Pole into maximum exposure to Sol for the first time since before anyone could measure what that means. The atmospheric circulation patterns should shift. Storm activity should change. The polar vortex Hubble confirmed in 2022 should evolve as the geometry of heating changes. The auroral bands, Webb mapped in 2025, should respond to altered solar wind angles as the magnetosphere's orientation relative to the incoming particle stream rotates. Should? That word carries weight here. Every prediction about what Uranus should do has been calibrated against Voyager data that captured a single season under freakish conditions. The featureless blue disk, the compressed magnetosphere, the quiet atmosphere, all of it came from one snapshot of one hemisphere during one phase of an 84-year cycle. Scientists built 4 decades of models on that snapshot because it was all they had. Webb has already shown those models were incomplete. The storms were always there, hidden in wavelengths Voyager could not see. The magnetosphere was always active, masked by a solar wind event that squeezed it flat. The moons were always geologically alive, their surfaces too faint and too cold for 1980s instruments to interrogate properly. But even Webb has only observed Uranus during a narrow window approaching solstice. What the planet looks like at peak northern summer, how its atmosphere redistributes energy when one pole receives continuous starlight for years, whether the cooling trend in the ionosphere reverses or accelerates. None of this has been measured, ever, by anyone. The 2028 solstice is not just another date on an orbital calendar. It is the first opportunity in the history of astronomy to watch Uranus enter a seasonal state with instruments capable of actually seeing what happens. And the predictions built on Voyager say one thing. The data Webb has already collected says another. Something will break. The polar vortex is where the break may be most visible. In 2022, a team using the Hubble Space Telescope confirmed what ground-based observers had suspected for years. A cyclonic system sat over Uranus's north pole, spinning in a tight, organized structure that resembled polar vortices on Jupiter and Saturn. The discovery itself was not shocking. Every giant planet with a visible atmosphere has some form of polar circulation. What was shocking was the timing. Uranus had been classified as atmospherically dead for decades. A polar cyclone requires sustained energy input and organized atmospheric dynamics. Dead planets do not produce cyclones. Webb's infrared images in 2023 added detail Hubble could not provide. The polar region glowed bright in near-infrared filters, particularly at 3.0 micrometers, where methane absorbs incoming light and makes the surrounding atmosphere dark. The bright polar cap meant methane was depleted there. Something was pulling methane-poor air from deeper in the atmosphere upward to the surface at the pole, a large-scale circulation cell that functions like a conveyor belt. Warm air rises at the pole, spreads outward, sinks at lower latitudes, and returns at depth. This is a functioning atmospheric heat engine. The 2025 auroral mapping added another layer. Paola Tiranti's team at Northumbria University, working under Henrik Mellin's program, found that the auroral bands clustered around the polar region but did not align perfectly with the vortex. The aurora traces the magnetic field. The vortex traces the atmospheric circulation. The two systems overlap but operate on different physics. Charged particles, spiraling along magnetic field lines, collide with hydrogen ions in the ionosphere, producing the aurora. Meanwhile, thermal gradients and Coriolis effects drive the atmospheric vortex. Both converge at the pole, but they are not the same phenomenon. This distinction matters for 2028. As the North Pole tilts further into direct starlight, solar heating should intensify at the pole. Basic atmospheric physics predicts the vortex should strengthen. More heat at the pole means stronger convection, faster circulation, a more vigorous cyclone. But the aurora depends on the solar wind and the magnetic field geometry, and those change on different timescales. The magnetic field does not care about seasons. The solar wind does not care about axial tilt. So the vortex and the aurora may evolve independently as solstice approaches, pulling apart two systems that currently overlap. Or they may not. The ionospheric cooling trend Webb measured suggests that the upper atmosphere is not responding to increased solar input the way models predict. If the thermosphere is cooling while the pole receives more starlight, the vortex may weaken instead of strengthen. The polar cap may dim. The storms may subside. Every expectation could reverse. Ground-based telescopes have tracked Uranus's brightness and cloud patterns through the approach to solstice, and the results are ambiguous. Some observations show increasing cloud activity in the northern hemisphere. Others show periods of relative quiet. the planet does not follow a smooth seasonal curve. It lurches, erupts, and goes silent in patterns that do not map cleanly onto orbital geometry. The 2028 solstice will not answer the polar vortex question in a single observation. Seasons on Uranus last 21 years. The vortex may take a decade to fully respond, but Webb will capture the inflection point, the moment when northern summer begins in earnest. Whatever happens at the pole in the years following that moment will either confirm or demolish the atmospheric models built since Voyager. And right now, those models are not holding up well. The energy question sits underneath everything. Uranus receives energy from our star. It generates some amount of internal heat. Those two sources must account for everything the planet does. Every storm, every auroral glow, every degree of temperature in the thermosphere. The budget should balance? It does not. Start with what comes in. At 19.2 astronomical units from Sol, Uranus receives about 1/400th the solar energy Earth does. That is not much, but it is not nothing. The energy drives photochemistry in the upper atmosphere, heats the sunlit hemisphere, and powers whatever seasonal dynamics exist. Ground-based and spacecraft measurements have quantified this input with reasonable precision. Now add internal heat. Jupiter radiates about 1.7 times the energy it absorbs from the central star. Saturn radiates about 1.8 times. Neptune, despite sitting farther out in colder space, radiates 2.61 times. These planets are cooling from their formation, releasing gravitational energy stored billions of years ago. The excess is measurable, consistent, and explained by standard models of planetary evolution. Uranus radiates roughly 1.06 to 1.15 times its absorbed energy, almost nothing. For a planet 14.5 times Earth's mass, this is not just low, it is inexplicable. Where did the heat go? A planet does not simply lose its primordial thermal energy. It radiates it slowly over billions of years, and the rate depends on mass, composition, and structure. Uranus has the mass. It has a similar composition to Neptune. Its structure, as far as anyone can model it, should allow heat to escape at a rate comparable to its near twin. But the heat is not there. The insulating layer hypothesis offers one explanation. If a giant impact early in Uranus's history created a compositional boundary somewhere in the interior, a sharp transition between the hydrogen-helium envelope and the deeper ice mantle, that boundary could act as a thermal blanket. Heat from the core and deep interior would be trapped below it, unable to conduct or convect upward efficiently. The planet would appear cold from the outside while remaining hot inside. The missing heat is not missing. It is locked away. This hypothesis connects to the 2004 eruption. If internal heat is trapped, pressure from below builds over time. Periodically, the system may breach. Hot material from below the insulating layer could punch through in localized upwellings, driving sudden storm activity at the surface. The storms appear, rage for months or years, then subside as the breach seals. The planet goes quiet again. The cycle might repeat on timescales of decades or centuries, too long for any single observing campaign to capture fully. But the insulating layer hypothesis does not explain the thermosphere. 850 kelvins, roughly 577 degrees Fahrenheit above the cloud tops. If internal heat cannot reach the surface efficiently, it certainly cannot heat the thermosphere, which sits thousands of kilometers above the tropopause. The thermospheric heat must come from somewhere else. Auroral heating, gravity waves from below, charged particle bombardment from the magnetosphere. Every candidate has been modeled. Every candidate falls short by an order of magnitude or more. The energy books remain open. Two deficits on the same planet, one below the clouds and one above them, and no single mechanism closes either one. If the energy cannot be explained by what Uranus is doing now, the next logical step is to look backward. Something may have happened to this planet that reset its thermal clock entirely. the evidence for that something is written in the tilt: 97.77 degrees. Uranus does not spin like the other planets. It rolls. Its axis of rotation lies almost flat in the plane of its orbit, so its poles alternately face the central star and then face away across an 84-year cycle. No gradual process produces this orientation. Something violent happened. The simplest version of the impact hypothesis puts a single body, roughly the mass of Mars or larger, striking Uranus during the chaotic early solar system. Smoothed particle hydrodynamic simulations show that an impactor of 1 to 3 Earth masses, hitting at the right angle and velocity, can torque the planet's axis from a modest initial tilt to nearly 98 degrees. The simulations also show that such an impact would inject enormous thermal energy into the planet's interior, while simultaneously disrupting the internal layering. Some models produce a compositional gradient that traps heat below it. Others produce thorough mixing that should have released the heat long ago. The outcome depends on the angle, the speed, the composition of the impactor, and the state of young Uranus at the time of the collision, none of which are known. The ghost moon alternative, developed by Zeev Rogoshinsky and colleagues, avoids the impact entirely. In this scenario, Uranus formed with a massive moon, perhaps several percent of the planet's own mass, in an orbit that slowly evolved through gravitational resonance with our star. Over hundreds of millions of years, the interaction between the moon's orbit and solar tides gradually tilted Uranus's axis. The moon did not strike the planet. It pulled it sideways, degree by degree, across geological time. Eventually, the moon's orbit decayed. It crossed the Roche limit, the distance at which tidal forces exceed the moon's own gravity, and was torn apart. The debris either fell into Uranus or dispersed into a temporary ring that eventually coalesced into smaller moons. The ghost moon explains the prograde orbits of Uranus's 29 known moons. A giant impact should scatter debris into retrograde orbits, or at least into chaotic ones. But Uranus's major moons orbit in the same direction the planet rotates, in roughly the same equatorial plane. A slow, resonant tilt preserves these orderly orbits because the moons tilt along with the planet, gradually, over millions of years. They were never disrupted, but the ghost moon does not obviously produce an insulating layer. If no impact occurred, what traps the heat? One possibility is that the ghost moon's tidal interaction with Uranus during its long inward spiral heated the interior unevenly, creating compositional stratification through differential melting. Another is that the heat was never trapped at all, that Uranus simply formed with less thermal energy than Neptune due to differences in accretion history. Both ideas are speculative. Neither has been tested against the full suite of observational constraints. The most uncomfortable possibility is that both happened: an impact and a ghost moon, a collision that disrupted the interior and injected heat, followed by a massive debris moon that resonantly tilted the axis further before being destroyed. The evidence is circumstantial in every direction. The tilt, the prograde moons, the missing heat, the absence of the moon that should still be there. Each piece fits multiple stories. None of them fit only one. The magnetic field might be the sharpest tool for cutting through the ambiguity. Whatever happened to Uranus, whether impact or ghost moon or both, reshaped the interior. The magnetic field is generated in that interior. Its structure is a direct readout of what is happening below the clouds right now, and by extension, a fossil record of what happened billions of years ago. On Earth, the magnetic field is generated in the outer core, a layer of liquid iron and nickel, roughly 2,200 kilometers thick. Convection in this electrically conductive fluid creates a self-sustaining dynamo. The field is roughly dipolar, aligned within about 11 degrees of the rotation axis, and centered close to the planet's geometric center. It is, by planetary standards, tidy. Uranus's field is none of these things. The dipole axis tilts 59 degrees from the rotation axis. The field center is offset by roughly 1/3 of the planet's radius from the geometric center, and the field is not cleanly dipolar. Higher-order components, quadrupole and octupole terms, contribute substantially. The result is a magnetic field that looks nothing like a textbook example. It is asymmetric, complex, and generates a magnetosphere shaped like a corkscrew as the planet rotates. Voyager 2's magnetometer measured this field during the 1986 flyby. Those measurements remain the only in-situ magnetic data anyone has. Every model of Uranus's dynamo is calibrated against a few hours of data collected under anomalous solar wind conditions nearly 40 years ago. The diamond rain dynamo hypothesis offers a physical mechanism for the strangeness. As diamonds precipitate through the superionic ice mantle, they create compositional convection. Diamond-enriched fluid sinks. Diamond-depleted fluid rises. This circulation occurs in a medium that conducts electricity, the superionic water, where oxygen atoms lock into a crystal lattice, while hydrogen flows freely through it like a liquid. A conductive fluid in motion generates a magnetic field. That is the dynamo principle. But this dynamo operates in the ice mantle, not in a metallic core. It operates at middle depths in the planet, not at the center. And it operates in a medium whose conductivity, viscosity, and composition vary with depth in ways that laboratory experiments are only beginning to constrain. The 2024 experiments at the SLAC National Accelerator Laboratory and the European X-ray free electron laser showed that diamond formation begins at lower pressures than previous models predicted. This means the diamond rain zone extends to shallower depths in the planet. A larger rain zone means a larger region of compositional convection, which means a larger dynamo region. The 59-degree tilt and the 1/3 radius offset may be natural consequences of a dynamo that operates across a broad, off-center shell rather than in a compact core. The 2025 auroral mapping supports this interpretation indirectly. The auroral bands Tiranti and Mellin's team observed are consistent with a magnetic field that has strong higher-order components, exactly what a shell dynamo in the ice mantle would produce. A core dynamo tends to produce a clean dipole. A mantle dynamo produces a messy multipolar field. Uranus has a messy multipolar field, but consistency is not proof. The auroral data can constrain the field geometry at the surface. It cannot image the dynamo directly. It cannot confirm diamond rain. It cannot measure the conductivity of superionic ice at depth. For that, an orbiter carrying a magnetometer would need to spend years mapping the field from close range, watching how it evolves, searching for secular variation that would reveal whether the dynamo is stable or drifting. Webb can see the consequences. Only a spacecraft at Uranus can see the cause. The auroral map itself deserves closer examination. What Tiranti and Mellin's team captured during those 15 hours in January 2025 was not a static snapshot. Webb tracked the planet through nearly one full rotation, 17 hours and 14 minutes, and the auroral emissions shifted as Uranus turned. The bands brightened in some longitudes and dimmed in others. The pattern was not random. It followed the geometry of the magnetic field as different sectors of the magnetosphere rotated into and out of alignment with the incoming solar wind. On Earth, auroral ovals are roughly centered on the magnetic poles, which sit close to the geographic poles. The pattern is stable on short timescales. Observers in northern Scandinavia or Canada see the aurora in roughly the same part of the sky, night after night, varying mainly with solar activity. On Uranus, the magnetic poles are 59 degrees from the rotation axis and offset from the planet's center. As Uranus rotates, the magnetic poles swing wildly relative to the direction of incoming solar wind. The aurora does not sit in a fixed oval. It migrates across the planet every 17 hours, tracing a path that depends on the instantaneous orientation of a lopsided, off-center magnetic field. This has implications that go beyond aesthetics. The interaction between the solar wind and a planet's magnetic field determines how much energy enters the upper atmosphere. On Earth, this coupling is relatively steady because the magnetic axis and the rotation axis roughly align. Energy input varies with solar activity, but not dramatically with rotation. On Uranus, the coupling changes every hour. When a magnetic pole faces the incoming solar wind directly, the magnetosphere opens and energy floods in. When it rotates away, the connection weakens. The result is a pulsed energy input, a planet that experiences bursts of magnetospheric heating, followed by relative quiet, cycling every 17 hours. Some models of Uranus's magnetosphere, built before Webb's observations, predicted this pulsing. The 2025 data confirmed it exists, but revealed that the amplitude of the pulses was smaller than predicted. The aurora was more uniform than expected. Energy distribution across the ionosphere was smoother. One interpretation is that the magnetosphere has internal processes that redistribute energy faster than the rotation drives asymmetries. Another is that the magnetic field structure, with its strong quadrupole and octupole components, creates multiple interaction zones that partially compensate for the rotating dipole. The auroral structure also bears on whether the magnetic field is stable or evolving. If Uranus's dynamo is chaotic, driven by uneven diamond precipitation through a layered superionic ocean, the field could drift measurably over years or decades. Magnetic pole positions could wander. The tilt could change. The offset could shift. A single 15-hour observation cannot detect this, but repeated observations over the remaining lifetime of Webb, potentially through the late 2030s, could reveal secular variation. If the field is drifting, it would confirm that the dynamo is actively turbulent, not frozen in a steady state. It would also mean that every Voyager-era measurement of the field describes a configuration that may no longer exist. The aurora is a window into the engine room. Through it, Webb glimpses the dynamo, the magnetosphere, and the solar wind interactions simultaneously. But the window is narrow and the view is indirect. What the aurora hints at, only proximity could confirm. The auroral bands themselves tell a more specific story than their mere existence suggests. When Paola Tiranti's team published the formal analysis in Geophysical Research Letters in February 2026, the paper laid out 3 confirmations and 1 overthrow. The confirmations came first. The ionosphere extends to at least 5,000 kilometers above the cloud tops, mapped through emissions from trihydrogen cation, the H3+ ion that forms when solar, ultraviolet radiation, and charged particles ionize molecular hydrogen in the upper atmosphere. Ion density peaks at roughly 1,000 kilometers altitude, consistent with models of photochemical production and diffusive transport. The average temperature across the mapped ionosphere is 426 kelvins, with a peak of 470 kelvins at 3,625 kilometers above the clouds. These numbers matter because they are the most precise measurements of Uranus's upper atmosphere ever obtained. Previous estimates relied on Voyager 2's ultraviolet spectrometer, which observed a narrow strip during the flyby, and on ground-based infrared spectroscopy that averaged across the entire visible disk. Webb's 15-hour observation, covering nearly 1 full rotation of the planet, produced a 3-dimensional map: latitude, altitude, and temperature, resolved simultaneously for the first time. The overthrow was in the temperature trend. For decades, models of Uranus's ionosphere assumed a straightforward relationship between solar input and atmospheric heating. As Uranus's axial tilt exposes different hemispheres to starlight across its 84-year orbit, the ionosphere should warm and cool in response. The geometry changes, the heating changes, the temperature follows. This is how it works on every other planet where ionospheric temperatures have been measured. On Uranus, the temperature has been dropping for more than 30 years. Ground-based observations beginning in the early 1990s detected a slow decline that did not reverse at equinox in 2007 and has not reversed during the approach to solstice. The ionosphere is receiving more direct solar energy now than at any point since the 1940s. It is colder than it was in the 1990s, when it received less. The February 2026 paper confirmed this trend and eliminated several possible explanations. Calibration errors in the ground-based data were ruled out by the consistency of the decline across multiple telescopes and techniques. Changes in solar activity were considered, but could not account for the magnitude or duration of the cooling. Seasonal redistribution of energy, where heating at one latitude might cool another, was tested against the three-dimensional map and found insufficient. What remains is a planet whose upper atmosphere has decoupled from its energy source. The ionosphere does not respond to the geometry of solar illumination on timescales of decades. Something else controls its temperature, and that something has been pulling heat out of the upper atmosphere steadily since before most working planetary scientists began their careers. The candidates are speculative. Energy could be conducted downward into the lower atmosphere through mechanisms not captured in current models. The magnetic field's complex geometry could channel charged particles away from the ionosphere rather than into it, reducing auroral heating over time. The composition of the upper atmosphere could be changing, altering its radiative efficiency. Each idea explains part of the trend. None explains all of it. The ionosphere paper did not resolve the cooling mystery. It sharpened it. The temperature is not just low. It is systematically declining in defiance of the most basic prediction anyone can make about a planet approaching its star. Whatever is happening inside Uranus, it reaches all the way to the top of the atmosphere. Step back far enough, and the investigation reverses. Every anomaly documented across these chapters, the tilted magnetic field, the cooling ionosphere, the missing heat, the superionic interior, the diamond rain, the unexpected moons, and active geology, all of it describes a single planet orbiting one star. But ice giants are not rare. They are the most common type of planet discovered around other stars. The Kepler Space Telescope, operating from 2009 to 2018, surveyed more than 150,000 stars and found that sub-Neptune mass planets outnumber every other category. Gas giants like Jupiter and Saturn are uncommon. Rocky worlds like Earth exist but are harder to detect. Planets in the mass range of Uranus and Neptune appear everywhere. The Transiting Exoplanet Survey Satellite, TESS, has confirmed the pattern since 2018. Current estimates suggest that roughly 1 in 3 solar-type stars hosts at least one planet in this size range. Scale that across the Milky Way's roughly 100 billion stars, and the numbers become very large. Yet we have exactly 2 ice giants to study up close. And until Webb, we had barely studied either one properly. Neptune received its own Voyager flyby in 1989, under better conditions than Uranus, but still a single pass with 1980s instruments. No orbiter has ever circled either planet. No probe has ever descended into either atmosphere. The 2 most common types of worlds in the galaxy are the 2 we know least about in our own solar system. This gap has consequences for exoplanet science. When astronomers observe a sub-Neptune transit, a distant planet passing in front of its star, they measure the starlight filtered through the planet's atmosphere. The absorption features in that filtered light reveal atmospheric composition, but interpreting those features requires models, and models require calibration against known examples. Uranus and Neptune are the calibration points. The hydrogen sulfide detection matters here. If ice giant clouds are dominated by hydrogen sulfide rather than ammonia, every model of sub-Neptune atmospheric spectra built on the assumption of ammonia clouds needs revision. The superionic ice research matters because it determines interior structure models. How much of a sub-Neptune is rock? How much is ice? How much is gas? Depends on what phases those materials take under pressure. If superionic water fills 60% of Uranus by volume, similar fractions may apply to billions of exoplanets. Their magnetic fields, their thermal evolution, their potential for surface conditions all follow from interior structure. The diamond rain matters too. Carbon is one of the most abundant elements in the universe. Methane is common in planetary atmospheres. If diamond precipitation is a standard process inside ice giants, then a substantial fraction of the galaxy's planets contain mantles enriched with diamond, driving compositional convection and generating magnetic fields tilted at steep angles. The chaotic, offset magnetic field Uranus displays may not be an oddity. It may be the default. Earth's tidy dipole, aligned with the rotation axis and centered in the planet, may be the exception. This reframing changes the stakes of every unanswered question. The cooling ionosphere is not just a puzzle about one planet. If the same mechanism operates on sub-Neptunes, it alters predictions about atmospheric retention, habitability of moons, and magnetic shielding across the galaxy. Uranus is the Rosetta Stone, and right now, the stone is only half translated. The contradictions have accumulated across this investigation without resolving. Line them up, and the picture does not clarify. It fractures. The thermosphere registers 850 kelvins, 577 degrees Fahrenheit, above the cloud deck. The effective temperature at the cloud tops is 59.1 kelvins, negative 346 degrees Fahrenheit. Both measurements are solid. The gap between them exceeds any known energy source's ability to explain. Auroral heating was the leading candidate until Webb revealed that even with active aurora, the energy budget falls short. Gravity waves propagating upward from the lower atmosphere could carry some energy, but models show they dissipate too low. Charged particle bombardment from the magnetosphere contributes, but not enough. The thermosphere is hot, and nobody can say why. Simultaneously, the ionosphere is cooling. It has been cooling for more than 30 years, while the planet approaches the portion of its orbit where solar input to the North Pole maximizes. The February 2026 paper confirmed that this trend is real, sustained, and unexplained. A hot upper atmosphere that is getting colder. Both facts coexist. Below the clouds, the planet radiates barely more energy than it absorbs, 1.06 to 1.15 times. Jupiter, Saturn, and Neptune all radiate substantially more, releasing primordial heat stored since formation. Uranus does not. The heat is either absent, meaning something expelled it billions of years ago, or trapped, meaning something prevents it from reaching the surface. If trapped, the insulating layer hypothesis works, but creates a secondary problem. Trapped heat should eventually escape through some mechanism on some timescale. No one has identified that mechanism or that timescale. The magnetic field tilts 59 degrees from the rotation axis and sits offset 1/3 of the way from the center of the planet. It may be driven by diamond rain through superionic water. This is consistent with laboratory experiments and with the auroral structure Webb observed. But no one has measured diamond rain inside Uranus. No one has confirmed superionic ice exists there. The laboratory conditions simulate Uranus. They are not Uranus. Ariel's surface carries carbon dioxide ice more than 10 millimeters thick on its trailing hemisphere. Carbon dioxide ice sublimates and breaks down under radiation on airless bodies. For it to persist at that thickness, active replenishment is required. Cryovolcanism, fed by a subsurface ocean, is the most plausible source, but no plume has been observed. No thermal anomaly has been detected. The inference is strong but indirect. The 2004 storm eruption produced more than 30 cloud systems, with winds approaching 900 kilometers per hour, roughly 560 miles per hour. The storms appeared after decades of apparent quiet and subsided without clear explanation. No trigger has been identified. No predictive model anticipated the eruption or its end. A moon that may have tilted the planet over hundreds of millions of years may have been destroyed crossing the Roche limit. The evidence is the tilt itself, the prograde moons, and the absence of a moon that orbital mechanics suggests should exist. The evidence is also the lack of that moon, which is hard to distinguish from the moon never having existed at all. Every answer Webb has provided across 3 years of observations has generated questions that Webb cannot answer from 1.5 million kilometers away. The central question, what is Uranus, is more complicated now than when the first infrared image landed in February 2023. The investigation does not converge, it expands. The Uranus Orbiter and Probe must launch by 2031 or 2032. This is not a preference, it is orbital mechanics. A Jupiter gravity assist, where the spacecraft swings past Jupiter to gain speed and bend its trajectory toward the outer solar system, is available during that window. Using it cuts the cruise time to roughly 13 years, with arrival around 2044 or 2045. Miss the window, and the next viable Jupiter alignment pushes launch to the late 2030s. Arrival slides past 2050. Some trajectories without Jupiter push arrival into the 2060s. The 2022 Planetary Science Decadal Survey, the document that sets priorities for NASA's planetary exploration program for the coming decade, ranked the Uranus Orbiter and Probe as the #1 flagship mission priority. Above Mars, sample return follow-on missions. Above Europa, subsurface exploration. Above Venus, atmospheric probes. The scientific community looked at every major target in solar system exploration and concluded that Uranus was the most important place to go next. Fiscal year 2026 allocated $10 million for pre-formulation studies. $10 million is enough to begin designing the mission architecture, selecting instruments, and evaluating launch vehicle options. It is not enough to build anything. The next phase, formulation and then development, requires billions. Current estimates place the total mission cost in the range of $2 to $3 billion, comparable to the Cassini mission to Saturn or the Europa Clipper, now en route to Jupiter's moon. The budget threat is specific and named. Mars sample return has experienced cost overruns that have consumed large portions of NASA's planetary science budget. Every dollar absorbed by that program is a dollar unavailable for the Uranus Orbiter and Probe. The two missions compete for the same finite pool of flagship funding. Webb has made the scientific case overwhelming. 3 years of observations have transformed Uranus from the solar system's least interesting planet into arguably its most scientifically urgent target. Active moons, a dynamic magnetosphere, an atmosphere that defies basic predictions, an interior unlike anything else in the solar system, the most common type of planet in the galaxy, and we have never orbited one or sent a probe into one. But the scientific case and the funding case operate on different logics. The decadal survey says go. The data says go. The launch window says go now. The budget says maybe. Uranus has waited since 1986 for a return visit. It did not know it was waiting. It continued rolling through its 84-year orbit, cycling through seasons no human observed, generating storms no instrument recorded, maintaining a magnetic field no magnetometer measured. The 2028 northern solstice will arrive whether a spacecraft is en route or not. The auroral bands will shift. The polar vortex will evolve. The ionosphere will continue cooling or finally reverse, and nobody will be close enough to know which. The question that opened this investigation was, what is Uranus? Webb gave partial answers and deeper questions. The orbiter would give better answers and even deeper questions. That is how science works. You do not reach the bottom, you reach the next layer. The next layer at Uranus is 13 years and 2.87 billion kilometers away. waiting for a launch that has not been approved, on a planet that has never stopped being strange, in a solar system that still has not explained its own third largest world.